So we have derived these equations for three-dimensional generalized Hooke's law. Right? It's, in the real world, you don't always need to use them. Since in some cases, in some specific cases, we can simplify them into two-dimensional cases. Okay, those are two-dimensional cases so that we can simplify them. We can simplify the three-dimensional equations into xy plane equations. Okay, here just we will introduce two situations. Okay, the first case is called plane stress situation. Then we will talk about a plane strain situation. Okay, the first one, the plane stress situation, is the case when one surface of the stress element is free of stress. The plane stress typically occurs in the seam plates or the surface of the solid component. Okay. In these cases, since we said the one of the surfaces or one of direction is free of stress, so we normally assume that the sigma z equals 0. Okay, so you have normal stresses along x and y direction, but no normal stresses along z direction. And the tau yz and tau zx also equals 0. So those are the conditions for plane stress situation. If a structural member can fulfill these conditions, you can consider, okay, this is a plane stress situation. Okay, as just mentioned here, for a seam plate, as shown on the right hand side, for the seam plate, if you have a element here, okay, you can consider that this is x direction and y direction. Okay, you don't have any stress along z direction, so this is a plane stress situation. Also on the surface of a structural member, I see a tube or a hollow shaft. Okay, on the surface, if you cut an element, you can assume that this is the x direction, the axial direction is the x direction, and this direction will be y direction. Okay, you can just simplify it. When the element is small enough, you can simplify it into a xy plane stress situation. Okay, if this is the case, let's see a seam plate here. If you recall in earlier chapters, we had a example in which I give you a seam plate as well as the loadings along x and y direction, and requested you to determine the deformations along x and y direction. Okay, if you recall, in that example, we actually repeated the process we derived the generalized Hooke's law. Okay, but here, since we already determined the three-dimensional generalized Hooke's law, you can see that we can simplify that. We can use a shorter version of it to solve this problem. Okay, if we have sigma z equals 0, okay, so you just logically you can get two equations. First of all, this is from the complicated three-dimensional generalized Hooke's law to a two-dimensional plane stress Hooke's law. Okay, you logically get these two equations first of all. Okay, this is actually what we derived in the previous example in earlier chapters. Okay, when you have the loading along x1 direction, how can we determine the strains and deformations along x1 direction? Okay, this is actually what we derived in that example. Okay, in these two examples, if you consider the strains as known values and the stress values sigma x and sigma y are unknowns, you can solve them, right? So two unknowns, two equations, you can solve them and get these two equations. Right. So why we still have the third equation here? Okay, this is just because of the Poisson ratio, right? Although you do not have any normal stress along z direction, but because of the deformations along x and y direction, you will still have strains. You will have deformations along z direction. Okay, so this is just get based on the third equation in the generalized Hooke's law. You just remove the sigma z atom, so you get a shorter version of it. So in a plane stress situation, your Hooke's law, two-dimensional Hooke's law, describe the stress-strain relationships on the xy plane still have three equations, because you cannot ignore the strain along z direction. But the shear will be simplified into one, since your tau yz, tau zx both equal 0, so you have only one equation left. So the second situation is called plane strain. Okay, in plane strain, just one surface of the element, or better to say one direction of the element is free of strain. So normally we assume that along z direction, the epsilon z equals 0. Okay. Also, the gamma yz, gamma zx equals 0. Okay. In real world, the plane strain typically occurs in a very thick plate. Okay, that is shown here. It's a very thick plate. If this thing is very thick, you can ignore the strains along the z direction. Thinking about that in the real world, what other situations, structures, you can assume to be plane strain? Okay, one example given here is a dam. Okay, it's a dam. So normally a dam can be, the cross section of dam can be sketched in this way. Right? So your water pressure is added on this side. Okay, the water pressure is added on this side. So you can see that this is our xy cross section, xy plane. So thinking about that along z direction, perpendicular to this cross section, it's very long, right? This is a very, very long. Think about a Hoover Dam or Three Gorges Dam. Okay, it's very long along the z direction. So actually you can ignore the deformation and strains along the z direction. Okay, so this is why we can simplify it into a plane strain case. So how about other structures? Can you figure out other structures that we can simplify into plane strain? Especially students from petroleum engineering. Right? The pipes, but the casing, the gas pipes, or the casing in an oil well, gas well, or geothermal well. Okay, if you have this well, this casing or a tube, its cross section will be just like this. Okay, let's see. This is the x and the xy plane. Yeah, this is xy cross section. Okay, let's see. This is it's a pipe or a casing. Okay. So how about along the z direction? Along the z direction, it can be very long. It can be very deep. Right. The thickness of it is super large. Okay. So in this case, you can also ignore the deformations or the strains along the z direction. So we can also simplify it into a plane strain situation. Since we ignored the strain along the z direction, so our three equations in the generalized Hooke's law will be shortened into two. So you have only the two equations. Why not the third equation? Okay, because the third equation is just epsilon z equals 0. Okay, and since your gamma yz, gamma zx equals 0, so you have only one shear equation left. Okay, those equations can be used to calculate strains from stresses. So if you want to calculate stresses from strains, here are the three equations for plane strain cases. Okay, it is worth noting that the third equation can be simplified into a shorter version as shown here. Okay, now let's look at a simple example. Okay, in this first example, we will deal with a thin plate. Okay, a thin steel plate is subjected to biaxial stress. This is actually the same as the previous example in earlier chapters when I gave you the loading along x, y direction and request you to calculate the deformations along x, y direction. Okay, so the strain measured in the plate, see here, the strain measured in the plate had been given along x and y direction. Determine the stress along x direction, the normal stress, sigma x. Okay, I can also ask you to calculate sigma y, right? So you should know how to do that. Okay, if you look at this term measured, right? It's recall our last lecture. Like we use the strain row set. We use the strain gauges to measure the strains, normal strains along preset directions with known angles to the x direction. Then we can solve the equation. Right? We can determine the epsilon x, epsilon y, gamma xy, etc. Right? Then use it. We didn't talk about how to calculate the stresses, right? But here you should know with the generalized Hooke's law, how can we determine the stresses? Okay. So will we need to use the three-dimensional generalized Hooke's law? You can use it, but it will be more complicated. So the first step, we need to think about how to simplify it. Okay, since we just talked about plane stress and plane strain, okay, which situation does this one belong to? Is this plane stress or plane strain? Okay, look at here, we have sigma x, we have sigma y, but we do not have sigma z, right? Sigma z equals 0, okay? Is that plane stress or plane strain? Okay. The example given here is a seam plate. Okay, again, it's a seam plate. So obviously, the seam plate loaded along xy direction can be simplified into plane stress. Okay, you just need to use these two equations to do the calculation. Okay, since we only requested you to calculate sigma x, so you just use the first equation, and that will be enough. So here the equation, here let's write it here. First of all, this will be sigma x equals E over 1 minus Poisson ratio square epsilon x plus nu epsilon y, right? So this is the equation. Okay, the epsilon x is here, epsilon y is here, but how about nu? We didn't give you nu, the Poisson ratio, but we had an equation in previous chapters, right? This is the correlation between nu, E, and G. Okay, that correlation said G equals E over 2 times 1 plus nu. Okay, from this equation, you have just recall the numbers. Just substitute the numbers in. 72 equals 190 over 2 times 1 plus nu. Okay, from here you can calculate that nu equals 0.319. Okay, with this value from this equation, you just get the numbers in. The sigma x can be calculated as E is 190 gigapascal. Let's convert it into MPa. It's 1000 MPa. Okay, over 1 minus 0.319 square times epsilon x is 698 plus 0.319 times epsilon y, that is 422, times 10 to the negative 6. Why do we need this? Because the unit here microstrain. Okay, this is because of microstrain. 1 micro is just 10 to the negative 6. Okay, here our result will be 176.1 MPa. Okay, so this is the unit from here. That's it.